Thank you. Hello, everyone. Welcome to my defense. I'm glad to see all of you today. And before I will start my introductory talk, I would like to introduce my parents, who are Chris Tubis and Marius Poplauskis. My thesis is called Non-Classical and Chaotic Motion of Two-Dimensional Light. And I think it's frozen.
We have to reboot. Never had this before.
Yeah, I have my laptop actually. Can you bring my laptop?
Yeah, but yeah, sure.
Yeah, just one moment. I need to switch off everything.
Don't start it. Don't start it. You have to stop it again.
Okay.
And first connect it.
Mm-hmm. Thank you very much. So, yes, my thesis is called Non-Classical and Chaotic Motion of Two-Dimensional Light. And in this work, I studied two very distinct phenomena and tried to answer on two main questions. The first one is how fast can a particle move within a classically forbidden region, or in other words, tunnel. And the second question is, in what ways can classical chaos manifest in quantum systems? So let's start with quantum tunneling. Quantum tunneling is probably one of the most known phenomena from quantum physics, and it was studied basically from since inception of quantum physics itself, so for almost 100 years. And the idea is that in classical mechanics, the particle can surmount the potential barrier if and only if it has enough energy to do that. Otherwise, it will be just bounced off. And in quantum mechanics, there is always a non-zero probability for particle to surmount the potential barrier, even if it doesn't have enough energy to do that. And probably many people are aware that this year's Nobel Prize in Physics was given for the discovery of macroscopic quantum tunneling in superconducting circuits for the experiments that were done more than 40 years ago. And people show that actually quantum effects can be observed in macroscopic systems. And I think, in my opinion, this year's Nobel Prize highlights the importance of fundamental research. Despite the fact that tunneling was well studied and understood, some aspects of tunneling still unclear. For example, speed of tunneling particles or tunneling time. And in our work, we measured speed of tunneling particles, and this is our measurement scheme. The most important part of this scheme is that we have coupled waveguides, and the second important part is that we can inject particles with different initial energies, so we can probe both classically allowed motion, so propagation inside potential step, and also classically forbidden motion, so decay in solution in potential step. And just by analyzing particle density inside coupled waveguide region for different initial energies, we can restore speed of tunneling particles. And in this case, coupled waveguide scheme, namely coupling constant, plays a role of a clock to measure speed. And this is our main result: speed versus kinetic energy inside the potential step delta. And on the right hand side of the graph, you can see positive delta, which represents classical motion. And on the left hand side, you can see negative delta, which actually represent quantum tunneling. And here we can see that the lower the kinetic energy inside the potential step, so the more negative kinetic energy of particle, the faster they move, or the higher their velocity. And this is our main result. And this is actually very counterintuitive. And moreover, our speed measurements can be considered as a possible test for Bohmian interpretation of quantum mechanics. Shortly, for classically forbidden motion, Bohmian mechanics predicts zero velocity, but as we saw from the previous slide, our measured speed is not equal to zero. This actually attracted a lot of media attention. For example, science communicator Sabine Hassenfelder even made a video about that. And the second topic, which is studied in my thesis, is chaos. Chaos is usually represented as a butterfly effect, when tiny changes can lead to huge consequences in complex systems. For example, butterfly flapping its wings somewhere in South America can trigger a storm somewhere in Japan. In terms of classical mechanics, it means the existence of sensitivity to initial conditions leading to exponential divergence of closed initial trajectories. And in quantum mechanics, actually, we have uncertainty principle, so we do not have a notion of initial conditions and trajectories. But at the same time, we have correspondence principle, which tells us that for large quantum numbers or for large energies, quantum mechanics should give same prediction as classical mechanics. And this suggests us that there should be some physical mechanism that can give rise to sensitivity to initial conditions in quantum systems. And that's what we tried to measure. We used a so-called quantum wedge billiard system, which you can see here. And we, in our system, could excite a lot of different states inside this wedge. And actually, this red circle represents pump spot position, so the position at which we can excite different states. And the idea was to compare two excitation schemes. The first one is resonant pumping, so the first picture, and we can see if we change pump spot position, the dynamics is overall smooth, and we do not see big changes in modes. But if you have a look to non-resonant optical pumping, we immediately see that overall the dynamics are very different, and we can see these uncorrelated mode jumps when we change pump spot position. So here we really show that it's possible to find a mechanism, like physical mechanism, which will trigger sensitivity to initial conditions or classical chaos in quantum systems. And yeah, let's summarize. In the first part of my thesis, we measured the speed of tunneling particles, and in the second part, we observed a transition between quantum and classical forms of chaos. And thank you for your attention. Thank you for coming. I'm glad to see all of you. Yeah, and I hope you will enjoy the defense.
specific.
I open this public meeting of the Doctorate Board of the University of Twente. I would like to express welcome to all of you and to friends and then also family members who are joining online. And then a special welcome also to the members of the committee, Professor Svetlana Girevich from the University of Münster, Professor Ewald Verhagen from AMOF and Eindhoven University of Technology, Professor Martin van Exter from Leiden University, and our internal committee members, Professor Claudia Filippi and Professor Alexander Brinkman. Could the candidate and the paronyms now come forward, please? Dear candidate, are you ready for your defense?
Yes.
Now may I ask Professor Verhagen to ask and start the opposition.
Thank you, Mr. Chairman. Dear candidate, let me start by congratulating you on the completion of this beautiful thesis. It contains really beautiful experiments, and I was very interested to read it, and I'm also looking forward to discussing it with you because, of course, I have some questions. I would like to start with a relatively simple and technical question, which is what is the relevance really of probing the systems that you study with using lasing? So could you have, for example, in the experiments that you show in chapter 3, also have done similar or seen similar results by just using coherently probing the states of a cavity?
Highly learned opponent, thank you for your kind words about my thesis and thank you for your question. Yeah, actually, your question is related whether the usage of laser is very important in our system. And I think in general, yes, because our system is a microcavity system, and one of the mirror can be additionally nanostructured to confine a light in a 2D plane to have these 2D particles when we can treat photons as 2D massive particles and really confine it in 2D structure. And having actually lasing is important because that's why this is how we can actually have and probe eigenstate for our system, because otherwise if you just drive this system just coherently, we can probe different states at the same time, so superposition, so it's not nice. We really need to prepare particle with exact kinetic energy.
I see. So it is so you say that if you coherently drive the system, you would excite multiple eigenmodes at once, and when you make it lace, it goes in one eigenmode. Okay, I understand. I have another question that is more broader, so to say, and it regards the first word of your thesis title, that is on here, non-classical, and then non-classical light specifically. When I think of light, then in a classical sense, then I think of waves and wave phenomena. Now, you seem to talk about non-classical motion by looking at light as particles in Z, which I would say is a quantum picture in itself. So, can you explain to me a little bit about the experiments that you do? Do you see them as non-classical, so intrinsically quantum phenomena, or are we doing a classical experiment on optical waves?
Yeah, thank you very much for this very relevant and good question. And usually people, there are a lot of definitions of quantum systems. Some people tend to consider quantum systems as systems when we have only one quantum or few quanta. This is not our case. We have many photons, many particles, but we tend to consider our system quantum because we really have this wave-particle duality in our system. Firstly, it is light, and yeah, it's basically can be explained by wave phenomena. But also, as I already told on previous question, we have this microcavity in which we confine the light, and we have this paraxial approximation, which actually allows us to treat our confined light as particles, because they have quadratic dispersion relation as for massive particles. So basically our photons are particles with a mass, and we can describe our system by Schrödinger equation.
You can, but the paraxial equation that you interpret as a Schrödinger equation is in principle one that you can completely define on Maxwell's equations, interpret in terms of Maxwell's equations alone. In other words, imagine a universe in which the value of h bar would be 0. Could you do your experiments or not?
Yes, we can do these experiments.
Yeah, I believe so too. So, so you use these experiments to some degree to also challenge interpretations of quantum mechanics. Now, isn't it surprising that one can do an experiment that one can do in a fully classical sense to challenge interpretations of quantum mechanics?
Yeah, thank you for this question. And yeah, I think we really describe our system via Schrödinger equation. That's why we can say that it's quantum. Yeah, but I know that many people consider a lot of experiments with light as analog to quantum experiments. Yeah, but because in many of these experiments, people really have this linear dispersion relation just for usual light. We really have 2D particles, so that's why I think it's very relevant to call our system quantum, and yeah.
Okay, thank you.
Experiments.
I would like to move on a bit to the figures 3.4 and 3.5 in your thesis, which show these beautiful experiments that are also central to your conclusions and findings there. And so you interpret these within the paraxial approximation as an excitation and a particle, if you will, rolling down a hill and being excited on the left and propagating to the right, etc. But I could, in principle, also try to understand a complementary picture where I have a cavity, right, and the photons are actually propagating, if you will, or bouncing back and forth between the mirrors, and leaving the cavity normal to the plane here. And then what one is studying is you had the transverse eigenmodes of such a cavity, and you're trying kind of imaging them. Is that also a way in which you equally see these results? So can you interpret them as the transverse modes that light fields propagating normal to the plane of the figure are populating?
Yeah, thank you for your question. Yes, indeed, we can interpret it as transverse modes that we excite in our cavity. Yes,
yeah, okay.
Definitely.
One thing that I was wondering about is the role of dissipation in this interpretation. So you say that the cavity has a lifetime or a decay rate of about 4 gigahertz or so. The coupling rate J0 is about 6 gigahertz. So these numbers are quite close and comparable.
Mm-hmm.
So now I can imagine that all of the states then in the cavity have a line width that is of that size, and basically, yeah, I get states that might be separated by 6 gigahertz due to this coupling that each also have a line width like that. So how important is it when you now start to laze in these particular modes to take into account the dissipation of this cavity for the profiles that you see, and in particular also for the derivations of the dwell time that you get from these kind of pictures?
Yes, thank you for the question. As far as I understand, you mean the role of dissipation, like cavity losses in our system. That's what you meant.
So exactly. And would the results look the same if the losses were lower?
Yes. If the losses will be lower, results will be quite similar. For example, we can see this picture 3.6. This is actually population in both waveguides, and in main waveguide and auxiliary waveguide, and we see actually here the influence of losses.
Mm-hmm.
Yeah, we see this decay, but if losses will be just lower, we will see just actually longer decay.
Yeah, I understand that, but if you then turn to the dwell time that you try to and the tunneling speed that you try to extract, you see that it actually becomes really subtle, right? You look at the quick turn up of the intensity, and to what extent does the fact that the modes are all broad, meaning that they can be excited over some finite range, play a role? Did you take this into account in the analysis? If you vary this in your theory, do the patterns change, etc.? This was the question I had.
Actually, we didn't probe cavity with other values of losses. Yeah, but in general, losses can be important for dwell time if it's very big losses. Yeah, especially for this tunneling regime when we have classically forbidden motion, because we really have this decay. And if it will be too much losses, this decay will be also overlapped by losses. But since we measure this decay constant, we do not see a big influence on...
Right, so in a fully closed system, all of your conclusions would still hold, is that?
What do you mean by fully closed?
So the unity reflectance of the mirrors.
Yeah, I think so, yeah.
Okay, thank you.
Professor Verhagen, are you satisfied?
I am, thank you.
Thank you. We will continue the opposition with Professor Gerevic.
Thank you very much. And dear candidate, first, thank you very much for the nice thesis and very nice result. It was a pleasure to read your PhD thesis. And I would like to start with results that you presented in chapter 4, where you also introduce the concept of chaos in classical and in quantum systems. And you mentioned that, okay, in quantum systems it's complicated to apply the concept of Lyapunov exponent, but you can use other characteristics as, for example, Low-Schmidt echoes. Can you elaborate on that and give us some connections how the Low-Schmidt echoes can be considered as a measure of sensitivity in a quantum chaotic system?
Highly learned opponent, thank you for your comments, and thank you for a question. And Low-Schmidt echoes is a concept when we actually do not change initial conditions, because we cannot change initial conditions in quantum system, but we can change, we can introduce some perturbation into our systems, and there are some models, I think quantum kicked rotor, when people really introduced these perturbations, and then they can follow how the system will react on these perturbations, depends on strengths of perturbation. And I think in this sense, this concept is very similar to the concept when we just change initial conditions.
And can you also use the same concept of Low-Schmidt echoes if you have an open quantum system?
Yes, thank you. This is a good question. Let me think. I think so. Yeah. Because we need to introduce some perturbation. Yeah.
Okay, thank you very much. You also mentioned in the beginning of chapter 5 that the chaos that you observed when you introduced non-resonant pumping it's different as the route to chaos that could be observed for the class C laser.
Yeah.
Can you comment on that? What would be the possible route for the class C laser, and why this route would be different from what you saw?
Yes, okay. So usually when we consider quantum chaos, when people consider quantum chaos, they actually think about structures of eigenstates and eigenvalues, like they try to analyze some spectra and so on. And yeah, and that also what we do in our experiments. We use these systems, quantum billiards, and this is actually Hamiltonian systems, so they characterized by momentum and by speed fully. Yeah, and for example, yeah, class C laser chaos is actually driving dissipative system, not Hamiltonian, and in this case we do not have like momentum or velocity. We only have some like three observables, like polarization, electromagnetic field, yeah, and population inversion. And yeah, and in these equations, in this differential equation that can trigger chaos for lasers, it's important to have nonlinearity. Yeah, yeah, but for quantum chaos, usually we use Schrödinger equation, and it's linear, so it has a little bit different nature.
That's true. However, when you introduce the non-resonant pumping, you also put your system in the framework of a non-linear system, because you have the gain saturation, you also have a medium, so you are more in the framework of the open quantum system, isn't you? So could you then kind of connect to the roots of chaos more characteristic for open quantum systems or for classical systems?
Yeah, actually it was our task to connect these two pictures. Yeah, because for classical chaos we usually should have some nonlinearities or complex geometries, but for quantum chaos we do not have this. And yeah, we try to connect it by the fact that we initially analyzed this quantum wedge billiards, for example, in which it's possible to obtain quantum chaos in the sense of structure of eigenstates, because it has chaotic eigenstates. But we also try to trigger actually classical chaos in our system, because quantum chaos was not a problem for, like, to observe. Yeah, and classical chaos is not easy to observe in such system. That's why we really compare these two excitation schemes, and the second one, non-resonant optical pumping, that gives us both nonlinearity and noise as in usual semi-classical laser theory.
Could you think how, in this case, you can formulate a concept like a Lyapunov exponent if you have the signatures of a classical chaos? Would it be possible?
Yeah, that's a good question. I think some analogies would be possible. Yeah. Yeah, especially. Yeah, I know that actually. Yeah, people actually introduce some Lyapunov exponents when they consider some yeah, quantum systems. Actually, because if you have some nonlinearity, you can yeah, calculate yeah, Lyapunov exponent.
And in general, what would be the role of this gain and loss dynamics for the results that you observed in the chapter 5? Would you say that it is triggering the observation of classical chaos, the fact that you are kind of weakly dissipative?
Yes, yeah. Yeah, it triggers classical chaos because it has both gain, nonlinear gain saturation, and noise. Yes. And it actually, having all these three things leading to yeah, this winner takes all scenario in mode competition, and actually we usually in our system we usually have only one mode one mode competition. Yeah.
Okay, I'm satisfied. Thank you.
Thank you, Professor Grevic. We will move on with Professor Van Exter.
Dear candidate, I also would like to congratulate you with your beautiful work. Nice system, studied both for the tunneling as well as for the chaos. I would like to start with the system itself, and in particular the key equation 1.15, which sort of describes how your microcavity can be mapped onto a Schrödinger type equation. It has some history, undoubtedly. I was missing some references maybe, but I'm mainly interested in the approximations that are used and the range of validity of this mapping from the microcavity system to the Maxwell to the Schrödinger equation.
Highly learned opponent, thank you for your kindly words about my thesis, and thank you for a question. And do you mean this equation 1.14 or 1.15?
In a way, both of them, because they are, let's single out 1.15. I mean, the derivation is for 1.14, and then 1.15 is sort of the quantum analog with also the Einstein coefficients.
Yes. So basically, this equation 1.14 was like derived based on the fact that actually we have this paraxial approximation in our cavity. So this k vector in plane, k vectors in plane, they are less than k vector in along optical axis. So basically all of our motion mostly happens along optical axis, so between mirrors. Yeah, that is why when we do some approximations which leads us to this energy dispersion relation, in which we have like photons with rest energy, also this kinetic energy terms and potential energy terms, and then we applied then we can recognize momentum operators, and we can apply this to wave function to have Schrödinger-like equation.
So what would you say is the range of validity of this 1.14? I mean, what criterion do we have to satisfy?
Yeah, the criteria is that actually the most motion should happen in between mirrors, not in plane. Yeah, this is the most. This is. Yeah.
Okay, perfect. And then this 1.15 sort of introduces the Einstein B coefficients. Is there also an Einstein A coefficient that I should think of?
Actually, when we consider these equations, your question is about should we introduce spontaneous emission?
Yeah, and where's the pump profile, for instance, in this equation?
Yeah, so usually in such types of equation, people introduce spontaneous emission as noise term, so as a stochastic term. Yeah, and about pump profile, this is equation. This is the next equation, 1.16. Yeah, here we have G, and G depends on X, Y, so like where we actually pump, and also on time. So
Okay.
Yeah,
because I must admit that I had to read the thesis twice to understand what you exactly did. I mean, you say in chapter 3 that you measure at 1,000 different positions of the pump, and then I wondered, okay, what does the emission see? I mean, how much loss is there? Is the medium transparent enough, or is there a sort of emission and reabsorption of the photons? I mean, it probably depends on which regime you operate in.
Yeah.
But what can you tell me about that distinction between, say, the emission reabsorption on the one hand and the transparent medium regime on the other hand? Are you always in the transparent medium regime?
No, we actually, if we pump our system non-resonantly, we are not in transparent regime, so it's always some absorption and re-emission. This is the way in our system how we can have lasing. Yeah, we always have this, conversion, frequency conversions. Yeah.
But still, the emission propagates apparently pretty far in this double waveguide
Yeah.
configuration.
Yes.
Is it because you pump a longer region of that double
No,
waveguide?
we pump only in one place. Yeah. And because we have this potential landscapes, light can propagate to the potentials which has lower energy. Yeah. But we pump in just one place.
And absorption of the dye is no issue apparently.
Yeah.
Okay. Okay, then I would like to ask something about the dwell time that you study. In particular, on page 37, for instance, there is a logical equation like, okay, the dwell time is some sort of propagation length divided by the velocity. And then I wondered, okay, which velocity? I mean, is it a phase velocity, or should I think of a group velocity? And I was in particular wondering because in chapter 2, where there are a couple of models to describe this, some of the models have derivatives with energy, which
Yes.
sounds like a phase velocity, but what can you tell me about that distinction?
Yes, so on page 37 we have this graph which represents dwell time that we measured, this blue dots, yeah. And this dwell time is the most known, it was calculated by the most known definition of dwell time. So basically it's just number of particles in the reservoir divided by flux, probability of flux. So in this case, to calculate probability of flux, we need to use velocity of particles that approach potential step. And this is actually, we can say that this is a group velocity. Yeah, we have standing wave before the step, and it's actually represent group velocity. But the second time, which represented by green dots, it's actually this semi-classical approximation where we have this wavelengths divided by by speed. Yeah.
Yeah, because if I would rephrase the question, then maybe if we go back to page 14, that is, which contains descriptions of the Bohm-Wigner delay time and the Pollack-Miller time, I see equations which have a derivative with E. And so that looks like something where frequency dispersion could be an issue. And so I wondered whether that is important in your experiment. I mean, in a way, whether you're allowed to use the refractive index only, or whether the frequency dependence of the refractive index would show up in some way or another. And I don't know the answer, I must admit. But
yeah, okay. Yeah, it's a very good question. Thank you. Firstly, you asked about dwell time, and dwell time is not tunneling time, because dwell time actually consider all the particles which were transmitted, reflected, both. And then you referred to Pollack-Miller time and Wigner delay time, which uses this energy derivative. Yeah. And all these times that I refer to in introductory chapter, they were all obtained for different physical models. And for example, Wigner delay time was obtained for a model that we have wave packet. And for this wave packet, this energy dispersion is very much relevant. And also for this Wigner delay, people use just barrier, not potential step. And this is even more complicated whole situation, because if you have a wave packet which hits a potential barrier, that it will be firstly reshaped because it has dispersion effects, and also it will be, some part will be reflected, some part will be transmitted, and we will have resonator effects, and all the wave function will be just, I don't know, smashed, and it will be hard to actually make some conclusions from this experiment. That is why in our case we do not have wave packets. We basically solve eigenvalue problems. So we really prepare our particles to have exact energy or exact kinetic energy. Yeah.
Okay, clear. Thanks for your answers.
Thank you, Professor Van Exter. We will continue the opposition with Professor Brinkman.
Dank u wel, meneer de rector. Dear candidate, let me also congratulate you on the beautiful piece of work. I have some questions about chapter 3, but it's mostly due to my own ignorance, given the fact that this has also been published in a very high-profile paper. If I look at figure 3.9, I see experimental data that you've obtained from this waveguide experiment, and I see a theory model that fits reasonably well, except maybe for the part close to delta being 0. Before, in chapter 2, you have derived a model, and one of the results is figure 2.9. And there I see a small plateau in the middle, which to me looks like the plateau you're looking for also to explain your data. Is this correct, or am I overlooking? Why did you not include your equation 2.22 to fit your data?
Highly learned opponent, thank you for your kind words about my thesis, and thank you for your question. And yes, you're right. Actually, we do have this plateau in both theoretical model and in both our observation. And this plateau, it can be explained as a measurement back action. Basically, when we have this coupling in between waveguides, and which is represented by wave vector k1, in limits close to delta equal to 0, it's the value of k1 is very much close to the value of k2. That's why we do have this plateau. But on this graph, we just did not represent it. Yeah, but it's here.
But in your model, on this figure 2.9, the plateau ranges all the way up till delta being 1 in units of h bar times your coupling constant, which is this 6 gigahertz.
Yeah.
But in your experiment, you're plotting a range that is much smaller than that. So is it then still the same plateau?
It's not actually smaller. It's also very close to -1 delta to +1. Yeah. If you will have a look on the upper axis.
Okay. And what is the bottom axis?
Bottom axis is just same axis, but in terms of okay, yeah. It's a I have here a mistake, because a bottom axis should be in millielectron volts. Yeah, it's not in
Okay.
h bar g naught. Yeah.
Thank you for clarifying this.
Thank you.
Solves this problem. Thank you. Mr. Chairman, am I allowed a second question?
Yes.
Then in your chapter 5, you have a kind of also has almost philosophical reasoning of how you picture a measurement as a kind of mode selection process, which goes quite gradual and develops. Now you say this could be an alternative maybe to like decoherence theory or this ETH theories that are also quite popular. But what's the difference?
Yeah, thank you for your question. You mean what is the difference of our picture, how we how we see the measurement process in our system in comparison with the coherence model?
For example, yes.
Yeah, in the coherence model, yeah, we have this interaction of a system with an environment. So a system entangles with an environment, and yeah, at some point it will be just collapse to one eigenstate. But yeah, in the coherence model, we do not really have a physical mechanism which will tell us what we will measure. So we don't know what we will measure. Yeah, after decoherence, because in our model.
But aren't both just different representations of a gradual coupling to other modes, right? Like external oscillators, a heat bath, your different modes.
Yes,
and in that sense, they're all the same, perhaps, right?
Yeah, but the coherence model itself does not give like a physical mechanism which will explain how actually a system collapse to this particular state. Of course, we have this Born rule, yeah, which tells us with which probability it should happen, but it doesn't give us mechanism. Yeah.
Okay, and is there then a way that your experiment actually can tell that apparently decoherence theory cannot be complete?
Yeah, thank you for your question. Yeah, I'm not sure about incompleteness of decoherence theory, and actually in our experiment we do not claim that we have something very general. Yeah, we just analyze how we can describe the measurement process in our exact system. Yeah, so yeah, our intuition does not really give you how it can be represented in different other different systems which are not similar to our system. Yeah.
All right. Thank you.
Thank you, Professor Brinkman. We'll continue the opposition with Professor Filippi.
Well, dear candidate, I would also like to congratulate you for the thesis. It raised quite a few questions and stimulated some studying, actually. So I was not so familiar with a Bohmian interpretation of quantum mechanics, okay? And so I understand that it poses some problems in your particular case, your semi-infinite step. But then I was thinking that if you go to an atom or to a molecule, you're really going to have a lot of regions where your kinetic energy, local kinetic energy, which we use as a signature of non-classical behavior, so you have lots of regions where this local kinetic energy is actually negative. Okay, so if you think, the electron-electron potential diverges, so your kinetic will have to compensate that and be negative. So would that mean that this Bohmian interpretation of quantum mechanics would fail in a similar way that for the system you have looked at?
Highly learned opponent, thank you for your kind words about my thesis, and also thank you for your question. Yeah, as you said, we made the conclusion that in our case, when we have a semi-infinite potential step, we do have the zero phase gradients. That is why actually Bohmian velocity is equal to zero. And I think in all other cases in which standard standard Gaussian equation from Bohmian mechanics, which will give zero phase gradients, also will mean that velocity is zero. Yeah, in all these cases.
So, okay, so it would create problem in interpretation in normal material, well, in real molecules and atoms. You're saying you will have problem with this interpretation.
I think so. Yeah.
Okay. so has not been discussed in the literature, or?
Actually, I'm not sure. I think it's probably was discussed in the literature, but I'm probably not aware about it so
No,
much.
it's okay. Well, it has, yeah, okay, so it has also other oddities. I was thinking, but probably similarly, okay, so if you're having a phase which changes, if you have a wave function which changes sign, your phase will change. And so also you're going to have divergences in this velocity, which is also quite, okay, leads to some strangeness, even if you want to describe it in a deterministic manner. Any thought about that?
Sorry, could you repeat your question?
Well,
please?
so if I take a wave function, so your wave function is just real, and you're having a zero velocity. But even in a situation where you have a wave function which is real but changes signs, like an excited state, like a fermionic system, you will have divergences of your velocity. Of course, the measure of it will be at the nodes. You will have divergences because you go from 0 to pi. And that's gonna create a very strange situation of a classical, deterministic particle which all of a sudden has an infinite velocity. So that's also quite odd. I don't know. So if you have given any thought, since you have nodes and everything, yeah.
Yeah, thank you for your question. And actually, in our system, we have this exponential decay in potential step, which is real, and it gives us zero velocity, zero phase gradients. But also, before the step, we have this, let's say, standing wave pattern.
Okay.
Yeah, as you said, this had this plus pi phase signs, and actually it also gives us zero velocity everywhere in the system, both before step and after step. Yeah.
Okay.
Yeah. In any case, if wave function is real, yeah.
Okay. Well, thank you. So again, due to my ignorance, so when are the situations where this interpretation is actually helpful, or can account for something which what we learn in quantum 1 cannot account for? So why introducing it? So what kind of what does it solve for us? Which kind of problems?
Yeah, thank you for your question. Actually, Bohmian interpretation of quantum mechanics usually it's considered to have to give same predictions as standard quantum mechanics. So it actually doesn't give much more prediction than standard quantum mechanics. But for example, people try to employ it, for example, also for some quantum chaos, because for example, in Bohmian mechanics, we do really have these particle pictures when we have particles with everywhere we have momentum, defined momentum, and position, and people applied Bohmian mechanics in very different situations, and it's thought to predict. It gives same prediction as standard Copenhagen interpretation of quantum mechanics.
Okay, so should only help our intuition then somehow by having a deterministic picture.
Yeah. It's actually good to have interpretation which can be deterministic and not random at core. Yeah.
Okay. Mr. Chairman, can I still ask a question? Or?
Yes, please.
I must actually. So I was also a bit confused about your billiard. Okay, so in your classical picture, of course, it's a closed system. The particles bounces off the walls, reflects. But then your system is actually, at least as regards the domain, I'm not sure about the energy, is actually open, meaning is much larger than the actual wedge you have. And if I understand correctly, what you're doing, you're actually putting some absorbing boundary condition to simulate this, to simulate the fact that the wave goes through. So the two systems are very different. I'm actually I can see that you find, numerically and experimentally a correspondence, but I I was surprised because the system is, because in one case you have reflection, in the other case you're having, I don't know how do you call it, absorption or anyhow loss of your wave function. So should I be surprised? Can you explain me why does the correspondence still hold?
Yeah, thank you for the question. Yeah, I used this simulation, this numerical simulation, mostly for visualization purposes. Actually, to simulate different eigenstates in different wedges, and whether they give like 100% same predictions as our experimental system, I do not know. But I also do not claim that it actually can be, it's 100% correct.
No, but I don't have a problem with your simulation. I have a problem more with a classical picture, which a classical object is very different, So you're having elastic reflections, and here you're having the waves going through your billiard.
Yeah, thank you for the question.
Thank you, Mr. Beadle. Could I ask the candidate and paranames to take their seats? So I adjourn the public meeting of the Doctorate Board of the University of Twente.
Please be seated.
I reopen this public meeting of the Doctorate Board of the University of Twente. May I invite the candidate and the paronyms to take their stand before this table, please. The Doctorate Board of the University of Twente, represented by us, has examined your dissertation and heard your defense. The Committee of Deans has decided, in accordance with Article 7.18 of the law on higher education and scientific research, to admit you to the degree of doctor. I request the promoter to carry out the appointed task.
Under the authority assigned to us by law and on behalf of the Doctorate Board, I grant you, Violetta Sharoglazova, the degree of doctor and all the rights that are attached to this degree. As evidence of this, we present to you this diploma, signed by the Director Magnificus, the Secretary of the Graduation Committee, and your promoters, validated with the seal of the University of Twente.
Dear learned Dr. Sharoglazova, let me congratulate you also on behalf of the university on your acquired dignity. From now on, you have the right to use the title of doctor. This title implies that society can rely on the quality of your judgment, that you will act with integrity and transparency, and that you will communicate independently about the results and the social relevance of your work. Value the doctoralis as an honorable distinction and a well-deserved prerogative, but always remember the obligations imposed by it towards the scientific community and society. Now I ask the co-promoter to give the laudatio.
Dear Violetta, dear colleagues, dear guests, it is a great pleasure for me to say a few words about your remarkable achievements, Violetta, and about how you have developed over the past 4 years. So when I think back over the course of your PhD, what stands out to me is your steady, thoughtful way of working. You approached your project with curiosity and a strong interest in understanding the underlying physics. You engaged deeply with the questions that arose, discussed them openly, and worked to move the project forward. What I always appreciated was that you were not satisfied with just obtaining a result. You wanted to understand the why behind it. One of your particular strengths has been your reliable sense for detail. When we worked on manuscripts together, you often spotted aspects that would benefit from clarification or refinement. Your careful feedback has consistently strengthened the quality of our work. Now I want to emphasize that all of this is, of course, also the result of teamwork. That's clear. So ideas are developed collectively, experiments are carried out jointly, and data are analyzed as a team. And many group members, such as Marius, Chris, Charlie, I think even Mario is there, have contributed in important ways to this. But today, naturally, the spotlight is on Violetta. So So let me now turn briefly to your scientific achievements. I think your results go far beyond what one typically expects from a PhD thesis. So they have not only deepened my own understanding of quantum mechanics, I'm convinced they present a significant contribution to the field as a whole. A major focus of your work was the physics of quantum tunneling. So you showed that tunneling phenomena can be viewed in a new way, not primarily through tunneling times, but through the speed of the tunneling particles. And this perspective complements established approaches in the field and connects back to foundational works by others. So the question of how long particles need to tunnel through a barrier has been debated since the early days of quantum mechanics, as you know. Your results offer a new, and I would say clearer way of thinking about this problem. I'm sure it will take some time until this perspective fully settles in within the scientific community. But for me, it's already clear that this work has the potential to substantially advance this long-standing debate. So equally impressive as are your results on the transition from quantum chaos to classical chaos, it has long been suspected that this transition is closely linked to the quantum measurement process, and this makes the topic especially relevant and fascinating because the nature of measurement in quantum mechanics remains one of its fundamental open problems. So with your experiments, you have provided a clear example showing that measurement processes can emerge naturally from the interaction of the quantum system with its environment. And particularly striking is the insight that an everyday process, such as mode selection in a laser, fulfills all criteria of a quantum measurement. So this allows us to follow in detail how a quantum superposition collapses into a single mode, and it demystifies, at least to some extent, a process that is often treated as somewhat obscure. So these findings reach far beyond what one normally expects from a PhD, so they open new perspectives on some of the most fundamental questions in modern physics. Violetta, I would like to congratulate you once again on your excellent work and your courage to follow new ideas. Thank you, and congratulations again.
So dear Dr. Sharoglazova, I would like to congratulate you again for this achievement from the university. And then I would like, on behalf of the NP department, also to congratulate you and also the co-promoters. Can I ask you now with the panel to take your seats again? So, a bit of information about the way we are going to leave the room. So we will leave the room led by the beadle, the young doctor with the paranames, and then the graduation committee, followed by the remaining guests. So I close this public meeting of the doctorate board of the University of Twente.